produces another vector. Okay, so let's take a look. So let's start with this question. If we have a vector, how do we construct a perpendicular vector? So first, let's talk about this in 2 dimensions. 2 dimensions, it's easier to draw and it's easier to solve. So as you can see from the picture, if you just have a single vector in 2 dimensions, it's very clear where the perpendicular vector goes. So it's already determined. So first of all, the notation, if you have a vector u, the perpendicular vector is u with that little cross. I think that's familiar from geometry. And we can say like u perp or u perpendicular. Okay. And there's the formula. So if you have a vector that's a comma b, the perpendicular one is negative b comma a. And this is, okay, and let me say, here's the proof. How do you show that 2 vectors are perpendicular?
Take the dot product and you see if it equals the 0 on the top.
Right, so you take the dot product, a comma b dot negative b comma a, negative ab plus ab equals 0. Proof, done. And one comment is you can multiply the perpendicular vector by any constant, and it'll still be perpendicular. Because first of all, multiplying by a constant doesn't change the direction, and it also doesn't change the dot product. So, here's a vector, 3 comma negative 4. Let's find a perpendicular vector. So what's a perpendicular vector? 4 comma 3. It's a short problem. Okay. And just because it bears mentioning, also negative 4 and negative 3. Now, that vector is going in the other direction, but it's still perpendicular, because all you've done is multiply by a constant where that constant is negative. So I just want to be clear. So technically there's you could have a perpendicular vector going up or a perpendicular vector going down. It's all fine. Okay. Next. How do we do this in 3 dimensions? So in 3 dimensions, this is a bit of a different question. So let me start off by telling you what we are going to do. We're going to define an operation between vectors, which produces a 3rd vector, and that 3rd vector will be perpendicular to both vectors. So, and let me tell you why this is the thing that we're doing. In 3 dimensions, why are 2 vectors required to specify a perpendicular vector? So we have to use some visualization for this. So what is perpendicular? In 3 dimensions, what's perpendicular to one vector? What kind of shape or object? It's a plane. So I'll do just a quick sketch of what that means. So if you imagine that we're in 3 dimensions here, so x, y, z. So if you have some kind of vector here, this plane is actually perpendicular to that vector. So an easier way to think about it is that if you have the xy plane, what's perpendicular to that is the z-axis. So that's sort of, think about it in reverse, but that gives you the conclusion that a plane, in 3 dimensions, a plane and a line are perpendicular to each other. So that construction is something that we're going to talk about soon. But for right now, we're going to talk about just making construction with vectors. So in order to specify one perpendicular vector, we're going to need two vectors. So why does that work? Well, if you have a vector like this and then a vector like this, although again it's hard to draw in 2 dimensions, right? Then that will specify a vector coming out of here that's perpendicular to both of those vectors. So, and a nice way to think about this is if you have the standard x-axis and the standard y-axis, then what's perpendicular to those things? It's the z-axis coming straight out at you in 3 dimensions. Okay. Okay. So now we're going to define that operation. Here we go. So the cross product of 2 vectors looks like this. Now that looks like a whole mess of notation. I'm going to give you a device to remember this. In the x component of the cross product, the input vector's x components are omitted. So the first component of in the result, the first component starts with the second component of u times the third component of v. So over here, component 1 is u2 times v3 minus u3 times v2. And notice that the indices cycle. So when you go down here, the second component starts with 2, comes with 3, then 1. So it's u3v1 minus u1v3. And then the third component after 3 comes 1, 2. So it's u1v2 minus u2v1. So I claim that this is actually the vector created this way is actually perpendicular to both u and v. And how would you prove that that's true? You take the dot product and you get 0. So that's a whole bit of algebra, and you can just do that and confirm it for yourself.
You take the dot product of those of u.
Of this solution and I.
Another important comment. Cross product only exists for vectors in 3 dimensions. This is only defined for 3-dimensional vectors. So I just want to make a side comment. If you know linear algebra, there's a handy way to remember the formula for the cross product. So I'm not going to teach you linear algebra right now, but if you know it, there's a handy way to memorize the formula. So if you know linear algebra, you can remember the formula for u cross v as this determinant. Okay. So I just want to mention that. Okay, so that's a side note. Now on with the calculus. Okay. So the cross product. So the first thing we learn about the cross product is that it produces a third vector, which is perpendicular to your 2 vectors. Okay, cross product has another pretty incredible property. So the cross product gives you a vector. If you take the magnitude of that result, of that cross product, it's the same as magnitude of u times the magnitude of v times sine theta for theta, the angle between them. Now, of course, this is super similar to what? To the dot product. The dot product gives you magnitude of u, magnitude of v times cosine theta. So this is, in a sense, this is the complement to that. Okay. So let me also say this. So when we take the cross product of two vectors gives us another vector. Well, a vector has a magnitude and a direction. And we've now just given, with these two properties of the cross product, we've described both the magnitude and the direction of that vector. The direction is, it's perpendicular to our first two vectors, and the magnitude is that. For your mathematical enrichment, I have here a proof of this last formula, the fact that the magnitude of the cross product is just magnitude of u times magnitude of v times sine theta. So it actually involves using the dot product. So as you can see, just as with most initial things in vector calculations, all you do is write everything down in the components and then move them around and rewrite stuff. And that's the proof. Okay. So now let's actually use this stuff. So, for these two vectors, let's find a vector perpendicular to both, and let's find the sine of the angle between them. So, how do we do that? How do you find a vector perpendicular to both vectors? Take the cross product. Okay. So again, let's go through how the cross product works. So the first component, and let me just make a note as I'm doing this. Here, I again find it very, very helpful to write the vectors as column vectors, because that lets you visually organize the calculation that you're doing. So for example, in order to find this first mystery component, I'm going to do this. This times this. What did I say? Minus this times this. Or minus those two. Okay. So, the first component is 3 times 5. Or actually, let me just write the whole thing. 3 times 5 minus 2 times negative 2. The next component, get rid of those, okay? The next component is going to be the middle component, so it's 2 times negative 4 minus, then I go up to cycle up to the first component, negative 1 times 5. Then the third component, I'm going to use the first two parts. So it's going to be negative 1 times negative 2 minus 3 times negative 4. So for the third component, we did this crisscross. And let me just make the comment, for the second component, we crisscross like this. For the second component, you crisscross like this, where you start with the third component and then cycle, but it cycles to the first component. So imagine that we've got the first component written again because it cycles. That's how I think of it. And the rest of the calculation is just arithmetic. So that gives 15 plus 4 is 19. Negative 8 plus 5 is negative 3. And then 2 plus 12 is 14.
And that's just the resulting vector. That's a perpendicular.
So this is the cross product, and we know that the cross product is perpendicular to original two vectors. So that's part A. So that was part A. So now part B. So find the sine of the angle between them. So how do we do that? Let's go. The formula tells us this. So there's a formula, and we're going to flip it around so we're solving for sine theta. So sine theta is the magnitude of the cross product divided by the magnitude of u times magnitude of v. So sine theta is just this divided by this. So now let's work that out. So we know u cross v, so we're going to need the magnitude of 19, negative 3, 14. And then we're going to, actually, this is a little messy. Now it's going to be easier to write this as a row vector. Okay. So 19, negative 3, 14. And we want the magnitude of that divided by the magnitude of the first one, negative 1, 3, 2, times the magnitude of the second one, negative 4, 4, negative 2, 5. So now we just have to do a magnitude calculation, which is just basically the distance formula. So it's the square root of 19 squared plus 3 squared plus 14 squared. And it's true, I dropped the negative sign, but we're squaring it so it doesn't matter. And it's easier to, with the negative sign in there, it's just messier. So that's a little shorthand that I use to make what I'm writing down nicer. And then 1 squared plus 3 squared plus 2 squared, square root, times 4 squared plus 2 squared plus 5 squared, square root of all that. And that gives, whip out the calculator. So that gives the square root of, okay. So that gives you 566 square root over square root of 14, square root of 45. Okay. So, oops. Okay. So that gives square root of 566 over the square root of 630, which is approximately 0.948. And then if you're curious, we can actually figure out what theta is, and theta was
71 in grams, or 71.4 degrees, or 1.246 grams.
1.246, and that's in radians. And it was about 71 degrees. That's just a little extra. So that's the calculation. I want to talk about a nice picture now, which helps you visualize what's actually going on here. So imagine we have these two vectors, A and B, and we're taking their cross product. So what we saw is that if you calculate the magnitude of that cross product, let's go back to the formula. So if you take the cross product, take the magnitude of that, you get magnitude of u times magnitude of v sine theta. What does that represent? It's this picture. So if you think of the parallelogram formed by the two vectors, as in this picture, well, the length of the parallelogram is just the magnitude of A, and the height is the magnitude of B times sine theta, because you're projecting it onto that far side of the triangle. Well, what's the area of a parallelogram? It's the length times the height. So what you're actually calculating is the area of the parallelogram formed by the two vectors. So to review and bring it all together, the dot product of two vectors A and B gives you magnitude of A, magnitude of B, cosine theta. The cross product of two vectors gives you a vector. But if you take the magnitude of that vector, once again you have a number, and that number is magnitude of A times magnitude of B times sine theta, and that has a nice geometry interpretation as the area of this parallelogram. Okay. So, but once again, remember that the dot product gives you a number. Cross product gives you a vector, but in this case, we're taking the magnitude of that vector, which is now, again, a number. Okay. So now let's actually do let's do a calculation with this. Find the area of the triangle with these vertices. So hold on, I was just talking about parallelograms, and now this question's about triangles. So what do triangles have to do with parallelograms? It's half a parallelogram, exactly. So we find the area of the parallelogram, and we just cut it in half. Okay. So that's the first thing. So we know that the area of the triangle is half the area of the parallelogram in my nice little notation there. Okay, so that's the first thing. The second thing is, in order to do this, we need two vectors. But I didn't give you any vectors. I gave you vertices. So what I said was, and again, this is in 3 dimensions, so I can't actually draw 3 dimensions, so I'm just going to sort of draw like the general diagram. So if I've got 3 vertices that make a triangle, what we need for this calculation are 2 vectors. How can we do that? Yeah. There's a vector, and there's a vector. So the way that we define those vectors when we have a starting point and ending point is you just subtract. That was the very first thing we learned about vectors. So which points do you use? And the answer is, doesn't matter. So we can make any 2 vectors. So let's just do it however we like. So the vector PQ equals -3 minus 4, so that's -7. 5 minus 2 is 3. And then 1 minus 7 is -6. And let's say PR is 2 minus 4, so that's -2. 0 minus 2, that's -2. And then 2 minus 7 is -5. Okay. So now finally we have everything we need. We can actually do the calculation. So we need the cross. So it's -7, oops, -7, 3, -6, cross -2, -2, -5. It's a lot of negatives. Okay. So the first component will be 3 times -5 minus minus minus. That's going to be -12. So that's going to be -27. Actually, you know what? Let me just write it all out. Okay. -15 minus 12. And then the next one's going to be, you know, I'll just write out all the numbers. -6 times negative 2 minus negative 7 times negative 5. And then the next component will be negative 7, negative 2 minus 3, negative 2. Okay. So, and let me go back and do that for the first component also. This is 3, negative 5 minus negative 6, negative 2. Okay. So we do all the arithmetic here, and you get negative 27 and 12 minus 35, so negative 23, and then 14 plus 6, which is 20. So there's the cross. What we need is the magnitude of the cross. So now we need, so the area, let me actually go down. Okay. So the area, let's go right to the area of the triangle equals, we know it's going to be half of the magnitude of that. So we need half of that. So it's going to be the square root of 27 squared plus 23 squared plus 20 squared. So whip out the calculator, and you get so finishing up the arithmetic, you get the area as approximately 20.4. Okay. So notice all the steps. So I intentionally did like the hardest thing that this could possibly be to show you all the possible steps. So all the possible steps are, what if it's a triangle and not a parallelogram? You just need to take half. Well, what if I give you the vertices but not the vectors? Well, from the vertices you can make vectors, because the ending point minus the starting point gives you the vector, and you can just make two of those. And then you need to do the cross product, which gives you another vector, but then the magnitude of that vector is the area of the parallelogram, which then if we want the triangle, you just divide by 2. Okay, so that was a nice math problem. So now, as with the dot product, there were a bunch of properties of dot product. Now for the cross product, I want to show you a bunch of properties of the cross product. Okay. So I think the second one is the one that's the most obvious, which is that if you multiply one of the vectors times a constant, that's the same as multiplying your final result by a constant. That's number 2 right there. Okay. And so then here are all 6. So let's just make some comments. Number 1 tells you a really important property. Is cross product commutative? No. If you switch the order, you get the same thing, but it's negative. So this actually has a name. It's called being skew commutative.
What?
It's actually, the name is called skew commutative. You don't have to know that. I just mention it. Okay. So another thing is, let's look at property 3. Property 3, A cross B plus C, is the same as A cross B plus A cross C. So that is a familiar looking property. It says that cross distributes over addition. And number 4 is the same thing. It distributes on the other side as well. Well, expression 5 is actually what we're going to talk about right next. So it's actually related to an amazing property. So notice that the formula in 5 involves 3 vectors. So imagine that we have these 3 vectors in space. So in the same way that 2 vectors determine 2 vectors are, you can think of them in 2 dimensions, and that determines a parallelogram. 3 vectors in 3 dimensions determines this kind of solid. Looking like that. So first of all, identify, there's your vector, and your vector. So those 3 vectors form this solid, and this solid is called the parallelepiped. So name's hard to say. But the important, so I like to think of it as just like a leaning cardboard box. That's a nice way to remember it. Okay. So let's actually try to figure out something about this box, namely, what is its volume? Well, we can start with the volume that we know, or we can start with the thing that we know, which is we know the area of the base. The area of the base is just the B determined by the B and the C vector. It's a parallelogram. We know how to find that. You just do B cross C and you take the magnitude. So the only thing that's left is we need to figure out the height. So what's the height? Well, the height, you've got that A vector there. So the height is A times, what do we need? Cosine of theta. So where theta is the angle between A and what? It's not between B or C, but it's the direction that's perpendicular to both B and C. It's like another axis, in a sense. Well, how do we get the direction that's perpendicular to B and C? You take B cross C. So what we need is the cosine of the angle between A and B cross C. But that's so nice because we're already using B cross C in order to find the area of the base. So the volume of the entire thing is the magnitude of A times cos theta times the magnitude of B cross C. But look at that. That's just the definition of dot product. So it's A dot B cross C. Gives you the volume of the parallelepiped. Amazing. Let's do a problem for this. Find the area of the parallelepiped with these vector sides. So how do we do this? Well, it's just A dot B cross C. So we're going to do, sorry, that should say volume, right? Oh wait. I need 3, 2, 3 cross 4, 2, 0. Okay. So now we have to find the cross product. So it's going to be 2 times 0 minus 3 times 2. And then the second component is going to be 3 cycle round times 4 minus 3 times 0. And the third component will be 3 times 2 minus 2 times 4. So you got to work that whole thing out. You get minus 6, and you get 12, and then you get 6 minus 8, so negative 2. So you work the whole cross product out, and you get that. And now we have to finish by taking the dot product with the third vector. And that gives you negative 30 plus 36 minus 2. And that just gives 4.
No, wait.
So there's the volume. So if you like, so if we're saying this is meters, you could say these are cubic meters.
And you pick A, B, and C arbitrarily? Like, you make 5 feet 1 A.
So there's an important point here, which is, does it matter which vector is which? The answer is no.
Yeah. Because of the rule, it has to be because of the rule of this
Right.
somewhere, right?
So, right, so you could, because A, B, and C, we named those arbitrarily. You could just as easily make, if you go back to the picture, you could make this one C, this one C, this one B, and this one A. You know, it doesn't matter. You could name any vector whatever you like.
Yeah, but it has geometric coordinates, which
Right.
doesn't matter. It doesn't matter at the end of the day.
Okay. So that was another awesome math application of not just cross, but dot and cross working together. Next and last thing we're going to talk about with the cross product is an application that comes from physics. So this application, so we're going to come back to force, but in this case we're going to talk about torque. So I fully expect that nobody actually knows what torque is. So we're actually going to learn what torque is, and then we're going to learn how to calculate it.
The torque is the same one from physics? From this?
Yes.
No worries.
Okay, so let's take a look. So torque measures the tendency of a body to rotate around the origin, or to rotate around an axis. So a nice simple way to imagine this is imagine a wrench twisting a bolt. So the harder you push on the wrench, the more torque is applied to the bolt, the more the bolt is going to have a tendency to twist. Okay. So now let's make math out of this. So R, which we're going to write as a vector, we can also think of it as a point. So it's the point where the force is being applied. F is the force vector, and then we're going to have a new notation. T is going to represent our torque vector. Then very simply, torque equals R, which is like radius or a position vector, cross F, your force vector. Now, the axis of rotation is the direction of the torque vector. So the torque vector, if you like, will sort of point along the length of the bolt. And the magnitude of the torque is the magnitude of the torque vector. And so without going into what that means too much, the more torque you have, the faster the thing's going to spin around its axis. So let's see what it means to do a problem here. So a wrench is used to turn a bolt. The bolt is at the origin. The handle of, you've got a 0.3 meter wrench, is on the x-axis. So you apply 20 newtons of force in the downward, or in other words, negative z direction. So let's find the torque vector and its magnitude. So first, I want to direct your attention to this picture, and this is what this means. So, and in this case, I've moved the axes around just to make the picture a little nicer. So in this case, I've drawn the x-axis pointing to the right, and there's my awesome drawing of a wrench on a bolt. And I want to think of the z as going up and down on my sheet of paper. Not normally how we draw it, but it made drawing my picture a little nicer. Okay. So you're going to push down on the wrench in the direction. So first of all, notice that the wrench is 0.3 meters long on the x-axis, so I marked off 0.3. And you're going to push down on the end of the wrench. So you've got 20 newtons of force going in that downward direction marked by the arrow. Okay? So first of all, just using common sense, this means that the bolt is going to twist how? The bolt is going to be twisting around, as I've drawn it here, the y-axis. That's just common sense. So the only thing we don't know is what's the magnitude of that operation. So let's find these two things. So let's find the torque vector. So the torque vector is just the position cross the force. So what's the position? We have to write the position as a vector. Well, I said it's 0.3 meters out along the x-axis. So that just means this. The x component is 0.3, and the y and z components are 0. Now, what's the force vector? Well, we said it's 20 newtons in the downward z direction. So that just means that the z component is negative 20, and the other components are 0. Okay, so now we have those two vectors, and we take the cross product.
What did you get the one for?
Okay, so if you do the cross product, I'm skipping over the calculations. It's nice because there's lots of zeros in there, but what you wind up with is this vector, 0, 6, 0.
And that's the y direction. What does that mean in the y direction?
Exactly. Okay. So now, what's the magnitude of the torque vector? Well, it's the magnitude of the cross, which one way to calculate that would be to say the magnitude of the cross is just the magnitude of r times the magnitude of f times sine theta. So magnitude of r is just 0.3. The magnitude of the force F is just 20. And sine theta, theta is the angle between them. But we know that the r vector is in this direction, and the force vector is in this direction. They're perpendicular. So the angle is pi over 2, and sine of that is 1. So you work that out, and you get 6. Now, of course, that's the long way blindly using formulas. Alternately, you could say, well, here's my torque vector. What's its magnitude? It's just 6, all in the y direction.
What does that mean that it's in the y direction? What does it mean that it's going in?
So what does it mean to be in the y direction? So remember that the torque vector represents your axis around which your thing is going to spin. And we already said by common sense, we think it's spinning around the y-axis. We did the calculation. The torque vector is right there. So that's the calculation that shows that the bolt is spinning around the y-axis with a torque value of 6.